Alright, so for this video we're going to be doing something a little different, but it's also going to be like more of the same. Last video we did a problem with parallel circuits, and the one before that we worked with series circuits. Now what we're going to do is work with series parallel circuits. So, like before, what I have right here is a problem that I found on the internet in which we have a 24 volt source with two resistors in parallel, which is 100 ohms and 250 ohms, and then another set of resistors in parallel with 350 ohms and 200 ohms. So we're just going to recreate this over on our pad, and we can get started. So like before, I'm just going to draw it out. We have our voltage source. All right. And we have one resistor. And we have two resistors. Like this. Then it breaks out again. I have another resistor. We have our last resistor. Comes back together. And there. Okay, so now we have our series parallel circuit. And the values are 24 volts, 100 ohms, 250 ohms, 350 ohms, and 200 ohms. And we're looking for all the same things. We're looking for VT, V1, 2, 3, 4, IT, I1, 2, 3, and 4. Let's move this to the side a little bit. RT, R1, 2, 3, and 4. And PT, P1, 2, 3, and 4. Okay, so looking at our circuit right now, we have our system of resistors. This one and this one. If we could find a way to make this each resistor system the equivalent of one resistor, then we can treat it like a series circuit. To do that, we look at each individual resistor and see that they're in parallel with each other. Now, when you have resistors in parallel, the way you combine them is by adding the inverse value of the inverse sum. To do that, we take our first resistor. Let me work with this one first. Ideally, we're going to have one resistor of unknown value to represent the two resistors that are there. So we're going to take, like before, 1 over 100 ohms and add it to 1 over 250 ohms. And then we're going to take the sum and take the inverse of that. And that will be the value of the combined resistance. So let's plug it into our calculator. 100 1 over x plus 250 1 over x equals 1 over x. So the combined value of both resistors in parallel is equal to 71.428 ohms. So combined together, this resistor value is 71.428. All right. Now for the second resistor, or resistor system, let's just keep that and drag it down here. We're going to do the same thing. color it green. Let's do this green too, just keep everything there. Alright. Oh wait, no, this is going to be red, the bottom one's going to be green. There you go. We take 1 over our resistor value of 350. And we're going to add it to 1 over the inverse value of 200. And we're going to take the inverse sum of that. So putting that into our calculator, because ultimately we're going to be looking for one resistor value for both of the resistors, the inverse of 350 plus the inverse of 200, and take the inverse of that is going to be 127.27 ohms. So that's going to be the value of our second resistor pair. All right. So with that, we can redraw the circuit. Let's bring this down a little bit. And it will be accurate in its readings. This current circuit would condense into this. 24 volts. It'll be the same as a simple series circuit. You just have to treat it a little bit differently when it comes to our values, but for now, we can work at it like this. 71.428 ohms and 127.27 ohms. All right, so with this right here, we can find RT simply by adding 71.428 and 127.27. So let's find RT then. 127.27. Let's just double check. Plus 71.428. The total resistance value is going to be 198.698 ohms, approximately. And let's just write down our resistor values. It's going to be R1 is 100. R2 is 250. R3 is 350. R4 is 200. We know what our voltage is, 24 volts, and we don't know anything else. So let's start working. We need to find our current total, our total current going through the circuit. And to do that, we can bring up our triangle and cover up what we're looking for. In this case, we're looking for current. So that means we have to divide voltage and resistance. Our voltage total is 24 volts. And our resistance total is 198.698 ohms. Plugging that into our calculator, we get 120.78 milliamps. And that's going to be our current value for our IT. All right. So now we need to find how much voltage is going through each individual resistor. Well, each resistor pair, because we're stepping back from this. So to do that, what we do is take the current total and multiply it by the resistor. It's the same step as before. We're covering up the voltage, and we're going to be doing current times resistance. However, what we're going to do is multiply the current total. Let me just highlight that. The current total by this resistor value and not this resistor value, because if you remember, we combined it into one. And in a parallel circuit, because we need to treat it as a parallel circuit, the voltage is the same. Same voltage going down both sides. Current's going to be different. So that's why we are doing this the way that we are. So if you see, we have 120.78 milliamps going through the circuit. .78 milliamps. And it's being multiplied by the resistor pair that's equivalent to 71.428 ohms. And that's going to give us the voltage that's going through each component. So 120.78 times 71, made a mistake, 120.78 milliamps, and we're multiplying it by 120.78 milliamps, and we're multiplying it by 71.428, and that's going to give us 8.627 volts, and that's going to be the value for V1 and V2. 8.627 volts. And there's a way to solve V3 and V4 without calculation. I'll just show you the little shortcut. We see that the voltage total is 24 volts, and the voltage drops 8.627 volts. Now, if we just subtract 24 and 8.627, we see that we're left with 15.373 volts. So that has to be the value for VR3 and VR4. So let's just double check our prediction. I predict that it's going to be 15.373 approximately volts for VR3 and VR4. Okay, so to do that, we take our resistor value of 127.27 ohms, and we're multiplying it by 120.78 milliamps. Now plugging that into our calculator, 127.27 times 120.78, we get 15.371 volts. And I predicted that the voltage value will be 15.373, and the actual value is 15.371, which is close enough, which means our values are correct. Now, if you want the numbers to look right, you could use a shortcut. However, if you want the calculations to be right, you can do it the long way. I prefer to do the shortcut because it makes everything add up perfectly. Because if you add 18.627 by 15.373, it equals 24. But yeah, that's just a preference thing. So now we're looking for current. So to get I1, we need to take a step back and realize that the current is going to be different because it's in parallel. So the voltage is the same, the current is different. That means we need to divide the voltage by each individual resistor value. Like this. And just keep on going down. And this. Each one is going to have a different current value. So all we're going to do is take our voltage values, let's say V1, and divide it by R1 to get I1, V2 divided by R2 to get I2, and the same for 3 and 4. So plugging it into our calculators, we have 8.627 divided by 100. It's going to be equal to 86.27 milliamps. And we can do the same trick as before and subtract the current total by our current value. So I'd predict that 120.78 minus 86.27, that the I2 value is going to be 34.51. 34.51 milliamps. And we can just double check that by dividing 8.627 by 250. And our value is 34.508. But it rounds up to 34.51 milliamps. So you see, the trick works. It's just you need to know when to use it or when it's not going to work. Doing it for I3, we have 15.373 and dividing it by 350. And that's going to give us 43.922 milliamps. And the same for I4, we can just take 120 minus 43.922. And it's going to give us 76.078 milliamps. Just doing the calculations to support it, 15.373 divided by 200 is equal to 76.865. 76.865. Let me see something. 15.373 divided by 200. It's not as accurate as I would want it to be, but it's because we were rounding numbers weird. So as long as you do something, you got to be consistent. So if you use the shortcuts, you got to use it for everything it applies to. And if you're not using shortcuts, you can't suddenly use them because they'll throw off your calculations. It's just better to be consistent. So everything matches up. And now we got to go to the power. The power is going to be the same ordeal. You just need to multiply the voltage by the current to get the power. So 24 times 120 milliamps, 0.78. 24 times 120.78 milliamps equals 2.8972. Let's just round it. 2.89 watts. And 8.627 times 86.27 milliamps equals 744.25 milliwatts. 8.627 times 34.51 milliamps equals 297.71 milliwatts. And 15.373 times 43.922 milliamps equals 675.21 milliwatts. And 15.373 times 76.078 milliamps equals 1.1695 milliwatts. And let's just add everything together. No, not milliwatts, just watts. There you go. Let's just double check that. 15.373 times 76.078 milliamps equals, yep. And now let's just add everything together to see if it works. Let's add 744.25 milliamps plus 297.71 milliamps plus 675.21 milliamps plus I'm saying amps, but it's watts. 1.1695 watts. And it's going to be equal to 2.88667, which we can round up for this purpose as 2.89 watts. So it's going to be perfect. And that's how you do a series parallel circuit. Thank you, everyone, and have a great day.